Everyone talks about colonizing Mars, like it's just bigger rockets and a few domes away, but NASA's own data tells a very different story. In this video, we dig into NASA's real reports on radiation, landing, life support, power, food and law to show why. By NASA's standards, a self-sustaining Mars colony is still far beyond what humans can actually do today. NASA does not talk about colonizing Mars the way people do online. When you look at their public plans and technical reports, the focus is clear. Human exploration, initial crewed missions, and technology development to get people there, keep them alive for a limited time, and bring them back. The language is about test campaigns and risk reduction, not about founding a new civilization. At the same time, NASA states very clearly that turning Mars into something like Earth is not possible with present-day technology, and that long-duration human stays still depend on systems that have serious unresolved risks. So the real position is stricter and more technical than hype suggests. Visits may become possible, a colony is nowhere near justified by the data. That gap shows up even in the basic goals. NASA's current roadmap is built around proving a sequence of steps: survive deep space travel, land humans on Mars, operate safely on the surface, and get them home. Radiation, life support, landing, medical care, autonomy, power, and logistics are all framed in terms of how do we keep a crew alive through a mission. You do not see official timelines for 1 million residents or multi-generation societies. There's no serious NASA document saying, here is how we raise children on Mars, or here is how a Martian industrial economy replaces Earth's supply. Instead, you see a cautious effort to make the first missions barely acceptable in terms of risk. So what exactly is missing when people jump from visit to colony? Start with the simple ladder: a short expedition, a research outpost, a semi-permanent base, and a self-sustaining colony. NASA's near-term work sits in the first two rungs. An expedition means a small crew, a fixed duration, pre-packed supplies, and the assumption that the main job is to survive and return. A research outpost might rotate crews and lean heavily on resupply from Earth. A semi-permanent base would extend stays and push recycling and local resource use harder, but still assume backup from home. A colony is different in kind, not just in size. It has to handle births, childhood, chronic illness, surgery, aging, and mental health over decades. It has to grow food at scale, make spare parts locally, stay powered through long emergencies, and keep operating even if Earth support slows or stops. NASA's documents are very clear that they are not there. Food systems are still being tested for a few years of shelf life, not for generations. Life support is still being pushed toward high recycling rates for a small crew, not for a full town. Radiation limits are still defined around an astronaut's career, not around kids growing up in low gravity with constant cosmic rays. Power plans are about providing tens of kilowatts to a small mission, or maybe megawatts to a heavy industrial outpost, not managing a planetary scale grid. In other words, the official work is still about proving the basics for temporary human presence, not about closing the loop on an independent society. Underneath all the individual topics is a deeper issue. Mars is not one problem, it is a system of connected problems. NASA's Human Research Program groups the human side into 5 major hazards: space radiation, isolation and confinement, distance from Earth, altered gravity, and hostile or closed environments. That list is already serious, but the key point is how they interact. Radiation affects health and cancer risk, which affects medical requirements. Distance from Earth affects how fast you can get supplies and how much you can lean on mission control, which changes how autonomous crews must be. Altered gravity affects bones, muscles, balance, and circulation, which changes exercise demands, injury risks, and long-term health. Hostile environments and closed habitats affect air quality, microbes, dust exposure, and psychological stress. Solving one hazard usually pushes on another. Concrete example: add more radiation shielding. That means more mass. More mass makes the spacecraft bigger, demands more propellant, makes landing harder, and raises cost. You might then cut other redundancies to save mass, which hurts safety. Or think about high recycling life support. It reduces the need to launch water from Earth, but it adds technical complexity. That complexity demands more maintenance, more spare parts, more sensors, more crew time, and more robust power. On Mars, every extra device is one more thing that can fail when you are months from help. The result is that you don't have a neat checklist where each upgrade makes life simple. You have a tightly coupled system where each upgrade comes with a new penalty in mass, energy, maintenance, or risk. This is why we'll just figure out later does not match NASA's tone at all. The agency is conservative because it actually has to sign off on sending people into this environment. Their Moon to Mars health and architecture papers talk again and again about unknowns and partial solutions, radiation shielding that only cuts galactic cosmic rays by a small fraction, landing systems that have never delivered human-class masses to Mars, life support designs that are still being refined on the International Space Station, medical support concepts that struggle with distance and delay. Under current rules, NASA already has tight limits on acceptable risk to astronauts. A true colony would need those risks driven much lower, not higher, because the exposure is lifelong and multi-generational. So the honest evidence-based statement right now is not Mars is impossible forever. It is a self-sustaining Mars colony is not possible with today's demonstrated technology, risk limits, and operational experience. The distance between we can maybe run a harsh, high-risk expedition and people can live there for life without constant rescue from Earth is enormous. NASA's roadmap reflects that reality. Mars is treated as an extreme rare frontier mission, not as a destination ready for mass migration. The core line that captures this is simple, and you will hear it echo through everything that follows. NASA is not declaring Mars off limits. NASA is showing step by step why colonizing Mars is still beyond current engineering, biology, logistics, and law. Every time you see a bold promise about millions of people on Mars, you can stack it against this quieter set of facts. The leading space agency on the planet is still trying to solve how to send a small crew there and bring them back alive. And all of this is before we even look closely at what Mars itself is like. Thin air, extreme cold, radiation, dust, toxic chemistry. The planet's basic environment is the first wall any colony idea slams into. If the systems picture already looks this fragile, what happens when you add the full brutality of the Martian surface on top? Mars is not a slightly worse version of Earth where you just put on a thicker coat and a better helmet. It is a fundamentally hostile world. NASA describes it as a cold desert with a very thin atmosphere made of more than 95% carbon dioxide, less than 1% oxygen, and a surface pressure under 1% of Earth's. In practice, that means three simple things. 1. You cannot breathe the air at all, it's both the wrong gas mix and far too thin. 2. Liquid water at the surface is unstable. It either freezes or boils away, so open lakes and rivers are off the table without heavy engineering. 3. The planet gives you almost none of the automatic protection you're used to on Earth. Here, our air pressure, oxygen level, and temperature range all sit in a narrow band that keeps your lungs, blood chemistry, and ordinary water in a safe state without any machines. Mars does not offer that baseline. Everything that keeps you alive has to be created and held in place by hardware. This is why NASA constantly talks about habitats, pressure vessels, suits, and controlled environments when it talks about humans on Mars. There is no step outside for fresh air. Outside is a low-pressure carbon dioxide fridge that will kill you quickly if your systems fail. And that is before you even start asking about long-term health. A colony would not just need 1 or 2 reliable pressure shells, it would need a whole network of them, living areas, workspaces, farms, industrial zones, all of them pressurized, sealed, monitored, repaired and protected, non-stop for years. On Mars, the planet itself never helps you, it only pushes back. The obvious question then is, if the air is already that bad, maybe at least the temperatures are something we can work with? They aren't. The raw numbers are brutal. NASA lists Mars surface temperatures from as low as around -176 degrees Celsius up to about 30 degrees Celsius. or roughly minus 284 degrees Fahrenheit up to about 86 degrees Fahrenheit in rare, favourable spots and times. Other NASA summaries put the average around minus 65 degrees Celsius, or minus 85 degrees Fahrenheit. So yes, for short periods in certain regions, you can get temperatures that do not instantly freeze everything solid. But that's the wrong way to think about it. A colony does not care about the warmest afternoon of the year. It cares about the full range that hardware and people must survive through day after day, year after year. For long-term survival, the real threat is the swing. Habitats, spacesuits, batteries, pipes, seals, lubricants, and fuel systems all have to work through repeated cycles of deep cold and relative warmth. Materials expand and contract. Some fluids thicken, others boil away. Metals fatigue faster. Plastics become brittle. Dust gets into joints and then freezes and thaws. On Earth, a bad winter storm is something you wait out and then repair afterward. On Mars, the normal environment is already beyond what most Earth hardware ever sees. For a mission, that means constant engineering overhead. For a colony, that means you are running a permanent fight just to keep temperature shocks from eating your life support gear. You might think lower gravity at least makes life easier. Mars gravity is about 0.38 g, roughly a third of Earth's. NASA uses a simple comparison. If you weigh 100 pounds on Earth, you'd weigh about 38 pounds on Mars. Intuitively, that sounds helpful for walking, lifting and construction. Moving heavy equipment would feel easier, falls might hurt less, jumps go higher. But for the human body, that nice-sounding detail comes with a problem. Your skeleton, muscles, heart, blood vessels and inner ear all evolved in 1G. Reduce the load and your body starts to adapt in the wrong direction for long-term health. NASA still treats altered gravity as a major hazard, not a solved condition. In microgravity, astronauts lose bone and muscle, their fluid distribution shifts, eyesight can change and balance systems get out of practice. Mars is not 0G, but it is not Earth either. At 0.38 G, the mechanical load on bones and muscles is much lower. That may slow down some of the worst 0G effects, but there is no evidence it fully prevents them over years or decades. So a colony is betting people's entire lives on a gravity level that has never been tested long-term for growth, pregnancy, aging, or chronic disease. Instead of gravity being a free stabilizing force, it becomes another unknown your medical system has to fight. If the air is bad and the gravity is uncertain, maybe the weather at least is gentle enough to ignore? Mars says no again. The atmosphere is thin, so individual gusts carry less force than on Earth, but dust behavior is mission critical. NASA reports that dust storms can cover large regions and can last for weeks or even months. In recent years, real hardware has paid the price. The InSight lander lost power as dust built up on its solar panels and sunlight dropped. The Ingenuity helicopter had to pause flights when conditions made safe operations harder. These are small robots with carefully planned operations. A colony would be far more exposed. For people trying to live there, a long dust storm is not just an interesting weather event. It is an exam for the entire settlement. Can the power system keep running if sunlight falls for weeks? Can radiators, filters and fans keep working when dust coats every surface? Can communication stay stable? Can heating keep habitats above freezing if the external conditions get worse than expected? A colony cannot say, "We'll just hunker down and wait." It has to survive the storm while still doing maintenance, raising food, handling medical issues and keeping people stable. Dust on Mars is both a mechanical threat and an energy threat. Put all of this together, a thin carbon dioxide atmosphere, less than 1% of Earth's pressure, extreme temperature ranges, low gravity, persistent dust, higher radiation, toxic surface chemistry, and resupply that is months away. Each factor on its own would already demand serious engineering. Mars combines all of them into one environment. That is why so much of NASA's Mars work is still focused on environment characterization before humans ever land, measuring the air, dust, radiation, chemistry, and seasonal changes in detail. They are trying to understand how bad the battlefield really is, and this is the key point for the colony question. Many popular Mars discussions talk as if you can treat the planet like a rough frontier site. Harsh, but basically workable if you are tough enough. That is not how NASA treats it. In NASA's framing, Mars is a place where the outside environment is always trying to shut your mission down. It is not one enemy, it is a cluster of enemies that never stop pressing. Before colonization is even a serious conversation, you have to accept that basic fact. The planet itself is the first and hardest barrier. If the local environment is already this unfriendly, what happens when you stretch a human mission across the enormous distance between Earth and Mars and you remove the safety net of quick rescue and instant communication? Mars is not just like going to the moon, but farther. The distance changes everything. NASA puts the Earth-Mars distance between about 53 million and 401 million kilometers, or roughly 33 million to 249 million miles, depending on where the planets are in their orbits. Add the full path out and back, plus time in orbit and on the surface, and a round-trip human mission climbs past 1.6 billion kilometers, more than a billion miles. That scale is not just a big number for a headline, it rewrites how you run a mission. Communications slow down, rescue becomes unrealistic, spare parts planning changes, medical support changes, and every single kilogram launched from Earth becomes far more critical because you are committing it to a multi-year, one-way logistics path before it ever helps anyone on Mars. This is why NASA does not talk about Mars missions the same way it talks about low Earth orbit or even the Moon. Near Earth, if something fails, you can often send help, launch a replacement, or in extreme cases bring the crew home in hours. Around the Moon, you still have the option of relatively fast return and frequent launch opportunities. With Mars, that safety model breaks. The distance is so large that light itself takes minutes to cross it, and rockets take many months. Once a crew commits to a transfer orbit, they are effectively locked into a long trajectory with very little flexibility. That forces a different mindset, designed for isolation from day one, because help is not coming quickly, if at all. NASA's own transportation studies say this in very plain language. For human Mars missions, there will be no way to abort quickly back to Earth, and on-demand resupply is not possible. That one statement alone is enough to damage most casual Mars colony ideas. On Earth, towns, oil rigs, ships, and even Antarctic stations survive because they are embedded in big backup networks. Airlifts, sea routes, nearby hospitals, spare parts warehouses, and emergency teams. A first Mars settlement would start in the opposite condition. The backup network sits tens or hundreds of millions of kilometers away. Launch windows are rare, resupply is slow and inflexible. Any serious failure has to be survived locally, with whatever you already have on hand. That lack of a quick return option also changes crew psychology and engineering trade-offs. You can't reassure people with, if something goes really wrong, we just come home early. NASA has to assume the crew is committed for the full arc of the mission, out, surface stay, and back with no fast exit. So redundancy, fault tolerance, and training all have to step up to a higher level than anything in current human spaceflight. For a colony, extend that idea from a few years to an open-ended timeline. You're asking a population to live permanently in a place where evacuation is not a realistic plan. On top of the raw distance, the timing itself is not under human control. NASA materials point out that good Mars launch opportunities come about every 26 months. That's set by orbital mechanics, not by our schedule. For human missions, planners have to find windows that work both for the trip out and the trip back. There are two broad options. You can choose a minimum energy trajectory with a longer surface stay, giving a total mission length of around 3 years, or you can spend much more energy and propellant on a faster trip with a shorter stay, bringing the total closer to 2 years. The shorter option is not free, comes with a sharp increase in vehicle mass and complexity. So Mars is not a destination you visit whenever you feel prepared. It's a destination you reach only when the geometry of the solar system lines up and you are willing to pay the energy cost. For a colony, that 26-month rhythm turns into a hard limit on how quickly you can adjust. Need a new part design? You can't just ship it next week. Need to rotate crews because of burnout? The windows are fixed. Want to expand faster than planned? The launch cycles and energy budgets still apply. Any long-term settlement plan has to be built around this slow, uneven beat of arrivals and departures. That alone puts Mars in a different category from any remote place on Earth. Distance also attacks one of the most important tools in human spaceflight: real-time ground control. NASA's hazard descriptions say Mars crews can face communication delays of up to about 20 minutes one way. That means a round-trip message, question, reply, follow-up can easily run 40 to 44 minutes, sometimes more. Some mission profiles also expect full blackouts for days to weeks when the sun blocks the line of sight. At those delays, Houston is no longer a live co-pilot. Ground experts can give advice, but not in the moment of a crisis. That delay changes authority on Mars in a deep way. The crew has to become its own mission control, medical triage team, maintenance authority, and crisis board. Procedures have to assume autonomy, diagnose, decide and act locally, then inform Earth later. For a small, highly trained astronaut crew, that is already a big jump in responsibility. For a colony, it becomes a social problem, not just a technical one. Who leads when you cannot wait half an hour for a comment from Earth? How do you manage disputes, law, and emergency powers in a place that can go silent for weeks at a time? Colonization is not just send more people and more machines, it also means building a governance system that can stand on its own under permanent delay. And distance does one more thing. It turns small problems into potentially fatal ones. On Earth, many systems look reliable because if something breaks, you can ship a replacement or send a specialist. A delayed delivery might be annoying, but it rarely decides whether a whole town survives. On Mars, every minor fault is filtered through distance and delay. A cracked valve, a bad batch of filters, a software bug, or a single bad medical outcome hits much harder when replacement hardware or expert help are months and millions of kilometers away. NASA's own framing of the distance hazard connects it directly to food, water, equipment reliability, and healthcare. Food stocks must last longer, because you cannot easily top them up. Equipment must be repairable with local tools and skills, because you cannot just ship a new unit on short notice. Medical emergencies have to be handled with limited facilities and no rapid evacuation option. The whole point of a resilient civilization is that it can absorb constant small failures without collapsing. Right now, Mars distance pushes in the opposite direction. It magnifies each failure instead of buffering it. So if distance already breaks the usual rules of human spaceflight, no quick abort, no fast resupply, no real-time control, what happens when you add one of the hardest hazards on top of that? Deep space radiation that hits you all the way there, all the way back, and even after you land. Radiation is one of the clearest places where NASA's view of Mars clashes with easy colonization talk. In NASA's own hazard list, space radiation sits as one of the 5 central dangers of human spaceflight, and they keep stressing that it is especially hard to solve. It is invisible, it never really turns off, and it damages the body over time at the level of cells and DNA. The 2023 Moon to Mars Human Health Report adds a key detail people usually miss. Normal spacecraft and habitat shielding work reasonably well against bursts from the sun, called solar particle events, but against galactic cosmic radiation, the constant high-energy particles from outside the solar system, the same shielding only cuts the dose by roughly 7% to 15%. That is a small reduction. It does not match the fantasy of thin-walled glass domes and light metal habitats scattered across open terrain. The result is simple and uncomfortable. With current materials and thicknesses, you are not turning deep space and Mars into a safe radiation environment. You are slightly reducing the dose in a field that is still strong. Those numbers also explain why NASA studies keep flirting with ideas like buried habitats, thick regolith shielding, and even large amounts of water or fuel as walls. If regular hulls only shave off a small slice of the most dangerous part of the radiation spectrum, then ordinary surface structures will not magically protect colonists who live there for decades. And this isn't just a theoretical worry. We already have hard data from hardware that went to Mars. During Curiosity's cruise, NASA JPL reported a galactic cosmic radiation dose of about 1.8 millisieverts per day inside the spacecraft's shielding. Later NASA graphics for a reference human mission, around 180 days out, 500 days on the surface and 180 days back, estimate a total dose of about 1 sievert for the whole trip, with similar contributions from each major phase: outbound, surface stay and return, so the exposure doesn't just spike in deep space and then disappear once you land. Mars reduces it somewhat, but not enough to make the surface feel like Earth. For context, 1 sievert is not instantly lethal, but it is a big dose in radiation protection terms. It's linked to a noticeable increase in lifetime cancer risk. That's for a single long mission. A colony involves people staying longer, going back and forth outside more often, and eventually raising children in that field. If you need multiple missions or long-term residence just to build up infrastructure, you start stacking those doses. On the surface, Curiosity's instruments have measured dose rates of roughly 210 micrograys per day, mainly from galactic cosmic rays smoothed over time. Mars's thin atmosphere does give some shielding, so it is better than pure deep space, but it's nowhere near Earth's level. There is no dense air column and strong magnetic field above your head to soak up the worst particles. In practical terms, living on Mars is not like living in a dry desert at high altitude. It is closer to working forever in an industrial zone, where a low-level radiation hazard is always on, and you can't ever fully walk away from it. NASA's own dose limits show how tight the margin already is before you even talk about colonies. Current human performance standards use a career effective dose limit under about 600 millisieverts and say exposures should be kept as low as reasonably achievable, the ALARA principle. Meanwhile, Curiosity's transit data suggested that just 360 days of cruise in that radiation environment, about a year or a round trip in deep space without counting the surface, could deliver around 662 millisieverts. The exact comparison is not one-to-one because models and shielding assumptions differ, but the basic message is blunt. A single Mars mission can push an astronaut close to or beyond what NASA wants to allow across an entire career. For exploration missions, NASA might accept higher risk for a small number of highly trained volunteers after long debate. For a permanent settlement, that logic breaks. You're no longer talking about a few people taking a one-time career hit. You are talking about a continuing population, living for decades in a radiation field that already stresses astronaut limits over a few years. The medical side of that is mostly unknown, and the early numbers are not encouraging. Once you treat radiation as a permanent background condition, the engineering options become very narrow. There are really only 3 broad paths. 1. Bring a lot more shielding from Earth. Thicker hulls, special materials, layered protection. 2. Use Mars itself as a shield by burying habitats under meters of regolith, or building them in natural caves and lava tubes. 3. Build thick, heavy structures on Mars using local industry, bricks, concrete-like materials, water tanks, or regolith blocks. All 3 paths are expensive in the same ways. They raise mass, they raise construction complexity, they raise energy demand, and they raise the maintenance load. That is why NASA's radiation discussion hits colonization so hard. It is not just a medical footnote, it is a tax on every design decision. Want bigger windows? Radiation gets worse. Want lightweight, easy-to-ship surface modules? Radiation likely gets worse. Want lots of surface time for farming and construction? Cumulative dose climbs. To get risk down, you end up driving your designs toward heavy, buried, or industrial-scale shielding solutions. Exactly the things that are hardest to deliver for a young outpost that depends on limited launches from Earth. And remember, all of this radiation exposure is happening on top of the distance, the hostile environment, and the limited rescue options you already saw. So the question becomes, even if you somehow protect a crew during flight and on the ground, can you actually land the huge, heavy hardware they need, safely and repeatedly, on a planet where we have never landed anything close to that mass with humans on board? Landing on Mars is not a solved problem that just needs a bigger rocket. NASA openly classifies it as one of the highest risk phases of the whole Moon to Mars plan. In its 2024 entry, descent and landing work, NASA points out that historically only 12 out of 19 robotic landing attempts have succeeded. That's with small unmanned spacecraft carefully designed for one specific job. Human missions are tougher on every axis. You have to land much larger masses. You have to hit tighter safety margins. You need wide, safe touchdown zones. And you're not landing just one rover. You need to land habitats, power systems, vehicles, cargo, and an Earth return system, often in a coordinated way. The more mass you bring, the harder landing becomes, and humans push you straight into the heaviest category. The core issue is that Mars's atmosphere sits in a bad middle ground. It is thick enough that you get violent heating and complex aerodynamics when you slam into it at the interplanetary speed, but it's too thin to slow very large, heavy vehicles down, using parachutes alone the way you might on Earth. NASA's own Adele analysis says that for human-scale payloads, you need advances in almost every part of the chain. Better atmospheric braking systems, better supersonic and hypersonic parachutes or alternatives, better rocket-powered descent, better guidance and navigation, and better models of how huge vehicles actually interact with Mars's atmosphere and surface at landing. In simple terms, the tricks that worked for small robots like Spirit, Opportunity, and Curiosity do not just scale up to multi-tens of tons human landers. Right now, every successful Mars landing has been a kind of one-off engineering shot. Each mission had its own lander design tuned to a certain mass and payload. That kind of approach is not enough for people. A crewed vehicle has to protect human lives, which means more redundancy and more structure. That drives up mass. As mass goes up, your options for slowing down get narrower and more demanding. You need larger heat shields, stronger structures, and more precise control, and you can't just accept a hard impact the way you sometimes can with a robot. Human-rated landing systems have to manage loads and accelerations within strict limits so that people walk away in good shape. And that's only for landing a single crew. Colonization changes the problem from a heroic landing to an industrial pipeline. A colony does not need one famous touchdown. It needs repeated, reliable cargo deliveries over years and decades. NASA's EDL work is explicit that heritage robotic lander designs do not meet the mass requirements of human-class Mars landers. That tells you right away that the colony story is blocked much earlier than people think. Before you talk about schools and farms, you need a way to put down safely the entire industrial stack. High-power reactors or solar arrays, big life support modules, greenhouses, mining gear, construction machines, ascent vehicles, scientific labs, spare parts, backup consumables, and more. All of that has to survive entry, descent, and landing, and much of it has to arrive before or along with the crew. There is also the question of where you land. On a map, Mars looks empty, but for engineering it is not empty in a useful way. Boulders, slopes, craters, and dust fields can wreck a landing. A crew cannot just set down anywhere and then drive a few hundred kilometers over unknown terrain to pick up cargo that landed far away. NASA's studies highlight the need to land humans and key payloads in close proximity to each other and to pre-selected infrastructure sites. That requires precision landing. Bleed off huge interplanetary speeds through a thin, tricky atmosphere, avoid hazards on the ground, and touch down in a tight zone. Then repeat that with heavy landers again and again without major failures. For a colony, this turns into a logistics network problem. You don't just get a landing, you need a freight system, repeated flights, consistent performance, and no more error bars. Every time a lander comes in, you want it to arrive where planned, with cargo intact without kicking up so much dust it damages existing structures, and without putting the crew in danger. Until that becomes routine, every landing is a gamble that could take out critical supplies or even people. NASA's current position makes this very clear. The agency is still in the stage of identifying and maturing the technologies needed to land the first human explorers and their immediate support hardware. That is already a big challenge. Human-class Mars EDL is still research and development, not a standard capability. Colonization, by definition, would require that capability to be not only demonstrated once, but scaled up, industrialized, and made highly reliable. So before anyone seriously talks about building a city, they have to face a simpler but unforgiving condition. We do not yet have a proven way to land the mass of that city's building blocks on Mars, repeatedly and safely. And even if you could somehow solve landing and drop huge amounts of hardware onto the surface, all of that material then has to be supported for years by a transport and logistics chain that fights long travel times and extreme mass penalties. So the next step is obvious. Does the transportation and supply side actually support a colony, or does it collapse under its own weight long before that? The basic transport picture for Mars already hits most colony ideas hard. NASA's own Mars transportation work says a typical human mission is about 2 to 3 years round trip, and that is roughly twice as long as our longest continuous human stays in space so far. Stretch a mission to that length and every system gets stressed. Food has to stay safe and nutritious for years, not months. Water recycling has to keep working without major failures for the entire mission. Medical supplies have to cover every likely problem with no quick restock. Spare parts have to cover years of wear. Psychological support has to handle deep isolation. Exercise machines, batteries, pumps, valves, and computers all have to survive long-term aging without outside help. Radiation keeps adding up the whole time. A colony doesn't reduce any of those needs. It multiplies them because now you're not planning for one 3-year arc, you're planning for life. You might think, fine, just go faster and shorten the mission. NASA's transportation studies make that trade-off very clear. You can design high-energy missions that reduce travel time, but you pay for it with a sharp increase in vehicle mass. Faster means more propellant, bigger tanks, stronger structures, and usually more complex propulsion systems. On Earth, faster shipping is a win if you can afford it. For Mars, urgency comes with a huge physics bill. The more you push down trip time to help with radiation and logistics, the heavier and more expensive the vehicles become. That hits you at launch from Earth, during cruise, and again at Mars landing. Now, layer on the brutal fact about mass itself. Every kilogram you send to Mars is not just a launch cost. It drives everything. You need structure strong enough to hold it, fuel to push it, landing systems to slow it down, storage and handling equipment on the surface, and then spares and tools to keep it working. Mass is also risk. More mass makes landing harder and can make failures more catastrophic. That is why NASA keeps talking about in situ resource utilization, or ISRU. If you can make oxygen, water or fuel on Mars, you don't have to launch every kilogram from Earth. But ISRU itself requires hardware, power and maintenance. Until Mars can supply a meaningful share of what you need locally, settlement is basically extended camping with a very long and fragile supply chain. People are used to a world where if you run low on something, you call a supplier, put in an order, and a few days later a truck, ship or plane shows up. NASA's Mars planning repeats the same message again and again. There is no quick abort, no on-demand resupply, and big communication delays on top of that. You cannot patch a bad plan by rushing extra cargo at the last minute. Historically, Earth colonies survived because they sat on rivers, near fertile land, along trade routes, or within reach of other towns. They could trade, migrate, or receive rescue. A first Mars outpost starts with none of that. The planet does not give you free food, free water, or nearby cities. Everything comes from a launch pad millions of kilometers away, in rare windows after years of planning. That reality forces NASA into a very conservative logistics mindset. Redundancy, spare parts, and margins are not nice to have. They are mandatory because mistakes stay with you for years. A colony idea that assumes we'll just import whatever we're missing is skipping the hardest part of the problem. Realistically, the early phase on Mars will look like a small, heavily engineered base, not like a growing town, because supporting even a small base stretches today's launch and logistics system. And this leads to the less exciting but critical truth. Colonization is, at its core, a shipping and transport story, not just a heroic exploration story. You need a whole economy of heavy cargo launches, reliable crew transports, proven return vehicles, high mass landing systems, and robust local resupply before you can claim Mars is open for settlement. NASA's current architecture does not see Mars as that kind of corridor. It sees Mars as a difficult mission destination. You send a carefully designed stack of hardware and people, they do a mission, and they come back. Until we have a transport system where sending large amounts of cargo to Mars is routine, affordable, and reliable, talk about a self-sustaining colony as ahead of reality. The basic logistics chain for people and hardware is still being invented. And even if you solved that, all those shipments are mostly there to support one thing: keeping humans alive inside machines that pretend to be an ecosystem, with almost no room for error. That raises the next hard question. Can our life support systems actually run close to perfectly for years at a time, in a place like Mars, without constant rescue from Earth? On Mars, the environment is not something you live in, it's something you build. NASA's life support system, ECLSS, has to do all the jobs that Earth's air, oceans, soil and climate do for you automatically. It has to hold the right atmospheric pressure, keep oxygen at safe levels, pull out carbon dioxide, move air around so people can breathe, manage humidity, handle waste, prevent fires from becoming disasters, and supply clean water. On Earth, that whole chain is spread across a planet-sized ecosystem plus a huge industrial base. On Mars, all of that is squeezed into hardware. Pumps, fans, valves, tanks, filters, pipes, sensors, software, seals, wiring, and the procedures to maintain them. That means daily survival in a Mars habitat is not set and forget. It is continuous machine operation. If a pump stops, a valve sticks, a sensor drifts out of calibration, or a leak opens up in a line you didn't know was weak, the system that pretends to be your atmosphere can slide toward failure. There is no outside air to dilute a mistake, no groundwater to accidentally refill your tanks, no rain to clean your filters. The habitat is a closed box, and whatever happens inside that box is on you. For a short mission near Earth, that's already demanding. For a multi-year Mars mission, it becomes relentless. NASA's own recycling targets show how harsh the numbers are. For deep space missions, they want life support systems that can recycle at least about 98% of the water consumed and roughly 75% of the oxygen from exhaled CO2. Recently, on the International Space Station, NASA announced they finally hit around that 98% water recovery target. That is a huge technical win, but listen to what it actually means. To even consider Mars missions, they needed a system that throws away only about 2% of its water instead of, say, 10% or 20%. On a planet where you can't just top off from a tanker, that missing percentage is the difference between surviving the full mission and running dry. And that's on ISS in low Earth orbit, with regular cargo flights bringing spares, experts on the ground watching every trend, and the option to send a crew home in a matter of hours if something goes really wrong. Mars will not give you that safety net. The targets NASA sets are not about comfort. They're about minimizing how much you have to launch from Earth and how much slack you need in your systems to avoid disaster. A Mars colony would have to hit or beat those recycling levels not temporarily but permanently, and do it with more people and more complex usage patterns. Mars also turns routine maintenance into something much sharper. On ISS, if a filter is clogging or a pump is wearing out, you can schedule a replacement on one of the many cargo vehicles. If a piece of hardware is outdated, you can send up a new version next year. If a problem gets complicated, experts on the ground can walk the crew through step-by-step troubleshooting with nearly real-time communication. On a Mars mission, NASA is already planning under very different rules. No chances to top off the water supply, no fast flights of replacement parts, long communication delays, and hard launch windows. So every leak, pressure drop, weird sensor reading, unexpected smell, bacterial bloom in the water loop, or strange software glitch has more weight. If a filter clogs on Mars, you cannot just say, "We'll swap it with the next shipment." You either fix it with what you have, improvise a new one, or live with degraded performance. If a CO2 scrubber starts drifting, you need the tools, the spare components, and the knowledge on site to fix or rebuild it. If a software bug randomizes a control loop, you may not be able to rely on someone at Mission Control to debug it live while the clock is ticking. The same goes for big things: a crack in a tank, a failing bearing in a main circulation pump, a bad batch of replacement parts. Mars forces you to treat maintenance like surgery, careful, prepared, and absolutely critical. On top of the mechanical side, closed habitats change biology in ways that add risk. NASA's human spaceflight research shows that living in sealed environments for long periods affects microbes and people. Microorganisms can behave differently, form tougher biofilms, and spread faster in closed systems. Human immune responses can shift, and stress hormones go up under isolation, disrupted day-night cycles, and crowded conditions. So your habitat is not just providing air and water. It is constantly shaping the crew's internal biology and health risk over time. That matters for colonization, because a settlement that can't manage its own indoor ecology is on a timer. Air chemistry has to stay in tight limits, not just enough oxygen, but also low levels of harmful trace gases. Water purity has to remain high, even as it cycles through drinking, washing, hygiene, and possibly agriculture. Microbial growth in pipes, tanks, and filters has to be controlled so it doesn't choke systems or make people sick. Waste has to be processed in ways that don't leak toxins or pathogens back into the living space. If those loops get away from you, you don't get a gentle warning. You get degrading health, rising infection risk, and vital systems slowly losing function. This is why just build a dome and plant some crops is so far from reality. A real Mars habitat is a factory-like system where biology and engineering are jammed together. You need people who understand both, how to tune filters and pumps, and also how to manage microbial communities, nutrient cycles, and contamination. If that expertise or hardware is missing, the environment that you depend on begins to drift. Because it's sealed, that drift does not get naturally corrected by a huge outside world. It just builds. Now scale that from a small crew to a colony. A few astronauts on a mission can handle strict rationing, intense maintenance schedules, limited food variety, and a relatively fragile system, as long as it holds together for the length of the mission. They are selected, trained, and mentally prepared for that lifestyle. A real community cannot live indefinitely in that mode. Kids, elderly people, people with health issues, and ordinary workers cannot all live in a constant emergency posture where every shower, every extra hour of exercise, every piece of laundry, and every farming cycle feels like it might break the system. A colony needs something else: comfort margins and robustness. That means extra capacity in air and water systems so small surges don't threaten safety. It means multiple independent loops or backup modules, so one failure doesn't risk the entire habitat. It means a culture of repair, where local shops can fabricate replacement parts, rebuild pumps, reseal valves, and maybe even print or machine new components when old ones wear out. It means sanitation systems that can absorb odd events, a broken pipe, a spill, a temporary contamination problem, without collapsing. And it means life support systems that can be expanded and upgraded over time as the settlement grows without needing a total shutdown. Right now, NASA is not at that stage. The current work is still focused on mission-scale life support, how to keep a small crew alive and functional for a limited mission duration with high maintenance and strict operating rules. ISS is the main testbed, and even there, crews rely heavily on constant Earth support. The move from mission scale to colony scale is not just a bigger version of the same machines. It is a change in philosophy, from systems that survive with careful expert babysitting to systems that can be maintained and evolved by a broader population under harsher conditions. This gap is exactly why NASA talks about sustained human presence and long-duration missions, but not about full independence. The evidence simply doesn't support the claim that we can run a complex, mostly closed life support ecosystem for decades in a place like Mars without heavy Earth backing. We are just now proving we can approach the recycling rates needed for a few years, with rescue and resupply a rocket flight away. So even if you somehow ship enough hardware and figure out landing and logistics, the day-to-day reality is this. People on Mars survive only as long as their artificial ecosystem runs close to perfectly, with very little room for serious mistakes, and that ecosystem runs on power, a lot of power, under dust, cold, radiation, and distance. So the next question is, what does NASA's own choice of power source tell us about how harsh Mars really is? NASA's own power choice for Mars quietly says a lot about how hostile the planet is. In 2024, when they laid out options for how to power crewed missions on the surface, they picked nuclear fission as the primary technology, not as a side experiment, but as the main power source. The official reason is direct. They want to reduce the risk of losing the mission. In their analysis, fission wins because it can run day and night, is less sensitive to dust and seasons, works at many different landing sites, and keeps generating through global dust storms. If solar power alone were comfortably reliable on Mars, they would lean on it because solar is simpler to explain and proven in space. The fact that NASA moves straight to nuclear for safety tells you that sunlight on Mars is not a stable enough lifeline for humans. This isn't about being anti-solar. NASA has flown solar-powered Mars missions for decades. The problem is that a human outpost has a completely different risk profile from a robot. If a rover loses power, that's a loss of hardware and science. If a crewed base loses power, it's life support, heating, air circulation, water processing, communication, and possibly radiation protection all at once. Fusion reactors, if designed properly, give a steady baseline output that doesn't care if the sky is dusty, if it's night, or if winter is setting in. That kind of stability is exactly what you choose when you look at Mars and conclude the environment is too unreliable to trust with solar alone. Dust storms show why this matters. NASA's Mars material notes that dust storms can last for weeks to months and can sometimes grow to cover the whole planet. In a big storm, sunlight at the surface can drop so much that solar output falls off sharply, even if your panels themselves are still working. In 2022 and earlier events, NASA's InSight lander repeatedly had to go into safe mode as dust built up on its solar panels and the available power dropped. The Ingenuity helicopter had to delay flights until conditions improved. For a robotic mission near the end of life, that's acceptable. For a crew and a settlement, it's not. A colony cannot accept a situation where a common seasonal event can starve its power system. On Mars, energy is not just a convenience, it is part of the life support chain. Every kilowatt runs critical systems, heaters to keep pipes from freezing, pumps to move water and air, fans to avoid CO2 pockets, control electronics, freezers for medicine and food, pressure pumps, communication links and possibly greenhouses and ISRU plants. If a dust storm cuts power deeply for weeks, you're not just dimming the lights. You're asking whether the base can keep breathing, drinking and staying warm. That is why in NASA's framing, Mars power is a life support problem first and a utility problem second. Now look at the scale. NASA's surface power decision paper says that even a modest short-duration human mission with a small crew needs on the order of 10 kilowatts of continuous power, minimum. That's roughly like running several small American homes full-time, but in a place where failure is lethal. As soon as you add more serious in situ resource utilization, making oxygen, water and the fuel from Martian materials, the demand jumps into the hundreds of kilowatts or even megawatt-class systems. That is industrial scale power, not camping gear. For a quick flags and footprints mission, maybe tens of kilowatts and aggressive conservation can work. You keep the crew small, keep equipment limited, and treat every watt as precious. But a colony needs something very different. It needs the kind of power you see in factories and small towns on Earth. Enough for mining, large oxygen plants, water treatment, big greenhouses, workshops, vehicles, communication networks, and backup storage. It also needs excess capacity and redundancy so that losing one unit does not instantly put everyone at risk. That's where reliability becomes a civilizational threshold. On a short outpost mission, you can schedule high-power tasks at certain times, delay non-critical work, and live with tight margins for a while. If a system is down, you can reshuffle activities and accept temporary limits. A colony cannot operate in permanent power emergency mode. You cannot casually postpone heat, water purification, air processing, medical refrigeration, pressure regulation, or radiation shielding. Those systems must run all the time, regardless of storms, seasons, hardware aging, or delays in replacement parts. NASA's documents keep coming back to two key words for Mars power: reliability and availability. It is not enough to have a generator that works in a lab. You need systems that can be transported, deployed, maintained, repaired, and possibly expanded in a harsh, remote environment with limited tools. On Earth, a regional grid smooths over a lot of trouble. If one plant goes down, others can pick up load. Spare parts can be trucked in, specialised crews can travel to the site. On Mars, a small group of people is responsible for maintaining whatever reactors, solar farms, batteries and distribution systems exist, with spares that have to be predicted and packed years in advance. This is where colonization talk usually gets quiet on details. People will say, we'll use solar and batteries, or we'll just have a bunch of reactors, but they skip the part where all of that has to be shipped from Earth, landed safely, assembled, operated, refueled or cleaned, upgraded, and eventually replaced. They also skip the cost of redundancy. A real settlement needs overlapping power sources and storage, multiple reactors or large solar fields, large battery banks or other storage, and maybe backup generators. All of that is mass, complexity, and maintenance. Every extra safety layer is another thing that can break and another set of parts you need to stock. So the power story becomes another filter. Mars is not just cold and distant. It actively punishes weak or fragile energy strategies. NASA's decision to go with fission right out of the gate is one of the strongest indirect arguments against easy colonization. If the environment were forgiving, if dust were a minor nuisance, and if thin air and long nights were no big deal, you could probably start with solar plus some storage and upgrade later. Instead, NASA's analysis says, in effect, for the first cruise, we are not comfortable relying mainly on sunlight. That's a strong signal. When your first serious human missions to a world require nuclear reactors just to keep loss of mission risk low, you're not looking at a place that welcomes big, spread-out, lightly shielded cities. You're looking at a place where even a small base must be surrounded by heavy, high-stakes infrastructure just to survive. And remember, even if you solve the power problem at a basic outpost level, that power mostly serves something else: life support and local production, especially in situ resource utilization. So the next question is, if we absolutely have to use Martian resources to make this even slightly sustainable, how far along is NASA really on turning Mars from a place you ship everything to into a place that can actually supply what you need? In situ resource utilization, ISRU, is one of the few areas where Mars settlement talk connects to real NASA hardware. The logic is simple. Earth cannot keep sending everything forever. If astronauts can make oxygen, water, or propellant directly from Martian materials, they cut the mass that has to be launched, ferried across space and landed. NASA's Johnson Space Center describes ISRU as a way to enhance sustainability and support longer missions by extracting and using local resources. For colonization, this is one of the only credible paths. At some point, Mars has to stop being a place where every important kilogram comes from Earth. But that is exactly why its current limits matter. When you look at what has actually been done, you see early prototypes and lab-scale chemistry, not a functioning industrial base. Take MOXIE, the Mars Oxygen In Situ Resource Utilization Experiment, which flew on the Perseverance rover. In 2023, NASA announced that MOXIE had successfully extracted oxygen from the Martian atmosphere 16 separate times. It pulled in carbon dioxide-rich Martian air, ran it through a solid oxide electrolyzer, and produced small but measurable amounts of oxygen. That is real progress. It proves that under real Mars pressure and temperature, you can turn local CO2 into O2 with a compact device. For future such crews, that's a valuable confirmation that the basic chemistry and engineering are sound. But MOXIE is also a reality check. It was a tech demo box, not a utility plant. It produced grams of oxygen per hour in short runs under controlled conditions, with Earth teams watching every move. A colony needs something completely different. A continuous, fault-tolerant, high-throughput oxygen and propellant system that runs day after day, year after year. It has to supply breathable oxygen, feed fuel production, and provide margin for leaks, emergencies, and expansion. It has to be repairable in place, and it has to be integrated into a broader network of pumps, tanks, pipes, valves, power, and monitoring. The jump from "we can do this 16 times with a small box" to "we can do this forever" at industrial scale is huge. Water is another place where the headline sounds easier than the engineering. Yes, Mars has water. Orbital data and landers have shown subsurface ice, polar caps, and signs of buried deposits. NASA's own recent work on detoxifying Martian resources points out that subsurface ice could help support human activities, but that same work also says the water and surrounding soil contain toxic perchlorates and chlorates, chemicals that are corrosive to equipment and hazardous to human health even at low levels. So Mars has water immediately becomes Mars has contaminated water locked in ice, mixed with toxic salts. For ISRU, that means the task list is long. You have to locate usable ice, dig or drill it out, bring it to a processing unit, melt it, filter out solid impurities, remove perchlorates and other salts to safe levels, possibly disinfect it, store it without losing it to leaks or refreezing, and then distribute it through your life support and industrial systems. Every one of those steps needs hardware. Miners, heaters, centrifuges or filters, chemical reactors, tanks, pumps, insulation, sensors and control software. And all of that hardware has to work on Mars under dust, cold and distance, with limited spare parts. The same pattern shows up for almost every local resource people like to list. Yes, there is CO2 in the air, ice in the ground, various minerals in the regolith, and possibly useful metals and silica, but none of these are in a form you can use directly. Oxygen has to be split off from CO2 or oxides. Metals have to be refined from ore. Regolith has to be dug, sifted and processed before you can use it as building material. Each chain is really an industrial flow chart: compression, reaction, separation, purification, storage and distribution. That's the step most colony talk leaves out. Local resources only matter if you also have local industry. NASA's ISRU work makes it clear that using Mars materials requires more than a shovel and a tank. You need compressors to pull in and pressurize the thin atmosphere. You need reactors to run chemical processes at the right temperatures and pressures. You need catalysts and membranes to make reactions efficient. You need heat management systems because reactors run hot and Mars is cold. You need purification units and quality sensors so you know whether your oxygen's clean enough, your water is safe enough, and your fuel meets spec. You need power systems to drive all of this, and you need maintenance capability to keep it going when something breaks. In other words, ISRU doesn't magically remove mass from the problem, it changes what you ship. Instead of sending all your oxygen, water and fuel, you now have to send the industrial kit that makes them. Machines, spare parts, tools, test equipment and trained people. That can still be a huge win in the long term, but only after you pay the upfront industry tax. Before Mars looks self-sufficient, it looks like an outpost covered in refineries and pilot plants that are themselves fragile and experimental. NASA's own language around ISRU reflects this cautious, early stage. Officials describe technologies like MOXIE as critical steps for a long-term lunar presence and as enablers for initial human exploration campaigns to Mars. They talk about reducing the mass launched from Earth and enhancing sustainability for missions, not about full independence or rapid colonization. ISRU is framed as a bridge from send everything to send less and make some things there, mainly to support the first few generations of missions. So the key distinction is this: ISRU is necessary for any realistic path to colonization, but the current state of the art is at the proof of concept and early engineering level. We have shown that the chemistry works, not that the whole industrial system is ready to run unattended at scale. Until ISRU plants can operate for years with high uptime, handle faults gracefully, and be repaired by local crews without constant Earth support, they are not a foundation for a civilization. They are experimental support modules for exploration. And that brings you to another basic survival need that ISRU only partially touches: food. Even if you can make air, water, and maybe fuel from Mars, people still have to eat every day for years. Food is mass, food is chemistry, and food is psychology. So the next question is, if resupply is rare and local farming is hard, can a Mars settlement actually feed itself in a stable, healthy way? Or does food become the quiet killer that keeps true colonization out of reach? For Mars, food is not a comfort detail you solve at the end, it is one of the core survival systems, and NASA treats it that way. Their Mars material is blunt. Astronauts on a round-trip mission will not get resupply flights bringing fresh food. No regular fruits, no emergency grocery runs, no top-up shipment if something spoils early. That single fact changes everything. Food is not just calories in a box, it is shelf life over years. Vitamin and micronutrient stability, protein quality, texture, menu fatigue, eating schedule, packaging mass, water needed to prepare meals, how waste is handled, how much time cooking takes, and what eating together does to crew morale. On Mars, every weakness in that chain hits health and performance directly, because you can't patch it with extra deliveries. NASA's food teams are already designing for timeframes that most people never think about. Their space food systems work says exploration-class foods for deep missions have to stay safe, nutritious, and reasonably palatable for up to about 5 years under tight resource limits. That's not buy a pallet of military rations and you're done. It's a long-duration chemistry and packaging problem. Vitamins break down over time, fats can go rancid, flavors change, textures degrade, and some compounds interact with packaging. You have to maintain enough nutritional quality so that 2 or 3 years in, people aren't slowly sliding into deficiencies or health problems, even if they're eating enough calories. There is also the psychological side. Eating the same textures and flavors over and over for years wears people down. NASA calls this menu fatigue, and it can lead to people unconsciously eating less, skipping meals or avoiding certain foods, which then feeds back into performance and mood. On Mars, where you cannot fix that with a surprise fresh fruit shipment, your initial menu design and storage plan have to carry almost all of that load. For a colony, this issue doesn't go away. It grows. You have more people with different needs, ages, and preferences, all living under stress in a hostile environment. Because long-term stored food alone is not enough for morale or health, NASA is already testing crop growth and integrated food systems in analogues. The Shapir missions, for example, use a simulated Mars habitat on Earth to study not just isolation and workload, but also how food supply and limited crop growth affect mission success. Crews do not get regular fresh deliveries. They live with what's inside the habitat and what they can grow under controlled conditions. That's a clear sign. The agency does not consider grow food on Mars to be a solved problem. It is still in the experimental stage, being evaluated with small crews in safe conditions before anyone risks it in deep space. And here is where the planet itself hits back again. Martian soil is not ready-made farmland. NASA-supported studies show that Martian regolith contains perchlorate salts at levels that are harmful or fatal to most life and that disrupt plant growth. Those salts are also toxic to humans and corrosive to equipment. So the fantasy of just planting potatoes in Martian dirt misses almost all the necessary steps. Real Mars agriculture would mean either removing toxic salts from large amounts of regolith or not using raw regolith at all for direct planting. You'd likely end up with hydroponics, aeroponics, or heavily processed substrates inside sealed greenhouses. That brings a whole new layer of systems, controlled environments for plants with precise temperature, humidity and CO2 levels, high-quality water with its own purification loops, nutrient solutions that have to be mixed, monitored and recycled, disease control for plant pathogens and pests in a closed loop, artificial lighting or carefully managed sunlight, and the energy to run all of that. On Earth, a big greenhouse or vertical farm is already an industrial project. On Mars, it becomes even more complex because every gram of hardware and every watt of power costs you more. So the honest description is that Mars agriculture, if it happens, will look like an advanced greenhouse industry wired into life support and ISRU, not like simple frontier homesteading. There is no dirt plus seeds equals farm here. It's more like industrial plant plus biology equals food factory, and that plant has to be designed, shipped, built, powered and repaired far from help. Now tie this back to colonization. A group that relies almost entirely on shipped food, with maybe a small supplement from the experimental crops, is not a colony. It is an outpost. Its survival depends on Earth continuing to launch large amounts of food on schedule for as long as the outpost exists. True settlement requires food independence or at least a very strong local production base. That means agriculture that can feed the population reliably, year after year, with local water, local nutrients, and locally repairable infrastructure. NASA is not there. Right now, they are still at the stage of designing multi-year packaged food, running analog tests on crop growth and menus, and even sponsoring contests for Mars meal plans and food systems. None of that is failure. It is simply proof that making a resilient food system for even a small crew is an open problem still being studied. A self-sufficient colony-scale food system is a step far beyond that. So we already have multiple red lines: hostile environment, distance, radiation, landing, logistics, life support, power, and now food. And we still haven't talked about what long-term Mars living does to the human body itself. If it's this hard just to feed and shelter healthy adults for a few years, what happens when you ask human biology to live, grow, and age under different gravity and constant radiation for life? NASA's own health documents start from one blunt point. Human bodies and minds evolved to live on Earth. Normal for us is 1G gravity, thick air, a global magnetic field, and low radiation. Mars gives you none of that. So a Mars mission is not just going somewhere new. It is putting every major system in your body – bones, muscles, heart, blood vessels, brain, inner ear, immune system, even your mood – into an environment they were never built for. That single fact undercuts a lot of casual Mars talk. You're not asking, can we build a house there? You're asking, can the human organism function there for years without slowly breaking down? On a full Mars mission, NASA points out that astronauts pass through 3 different gravity regimes. First, there is weightlessness during the long trip out and back. That's 0G, the same basic condition we see on the International Space Station. Then there is Mars itself at about 0.38 G, roughly 1/3 of Earth's gravity. Finally, if they come home, they have to readapt to full 1G on Earth again. Those are not small changes. Each shift means your body has to adjust fluid distribution, muscle use, bone loading, balance, and cardiovascular work. NASA treats this as a core hazard. Muscles weaken if they're not loaded, bones lose mineral density, the inner ear and balance system get confused. Blood and other fluids move differently, affecting vision and heart function. Right now, we have some data on how people handle shifts between 1G and 0G, mostly from ISS missions. We have tiny bits of information from short exposures to lunar gravity during Apollo, but nothing like years in 0.38 G. So for Mars, even the basic question, what does decades in 1/3 gravity do to a human body, does not have a solid answer. For an exploration mission, NASA can accept some uncertainty. They send very healthy adults, watch them closely, and bring them back for study. For a colony, that uncertainty is not about one trip. It's about an entire lifetime. To compensate for what we already know goes wrong in reduced gravity, NASA plans to use exercise as a required countermeasure, not as a lifestyle bonus. Their deep space habitation work says future crews will likely need to exercise for long periods each day, think hours, not minutes, to slow down bone and muscle loss. That needs treadmills, resistive devices, bikes, or more advanced gear, all designed to work in reduced gravity and inside a pressurized habitat. This has 3 big consequences for any settlement. First, time. If every adult has to spend a big chunk of each day exercising just to keep their body from degrading, that time comes out of work, maintenance, training, and rest. Second, resources. Exercise machines take mass to ship, volume inside the habitat, power to run, and constant maintenance. Third, planning. Schedules have to be built around exercise blocks, and if people skip it, the health costs show up months or years later. On Earth, most people can get away with being lazy for a while. On Mars, lazy means your bones thin, your muscles weaken, and your heart and circulation adapt in ways that could be dangerous. A lot of public optimism hangs on the idea that Mars's 0.38 G is good enough and solves most of the worst issues we see in 0G. NASA does not treat that as proven. In their hazard framing, anything that is not Earth gravity counts as altered gravity and remains a major risk. They are still studying how performance, health, and recovery change across different gravity levels. The honest way to say it is, Mars gravity is probably less damaging than 0G, but there is no evidence it is safe as a lifelong environment. It's better described as less bad, not healthy. That matters for colonization because you are not just talking about one tour of duty. You are talking about people spending entire adult lives in 0.38 G, and then, if they return to Earth, coping with a huge jump back to 1G. You're also talking about injuries and sickness in a body whose bones and muscles may not behave like they do here. How do broken bones heal in low gravity? How does long-term joint wear look? How do heart conditions progress? We do not have solid answers. And then there's the part almost no serious Mars health data covers yet: full life cycles. NASA's current Mars architecture focuses on adult crews, mission length, and safe return. Colonization would go far beyond that. It would mean pregnancies in low gravity plus elevated radiation. It would mean fetal development in an environment that has never grown a human before. It would mean infants and children developing muscles, bones, balance, and brains in 0.38 G, not 1G. It would mean chronic diseases and aging in a place where your immune system, hormones, and organ function are all influenced by altered gravity, closed habitats, and radiation. We do not know if human embryos can develop normally in reduced gravity. We do not know if childhood growth plates in bones behave the same way when loaded at 1/3 of Earth's weight. We do not know how decades of slightly elevated radiation and different gravity interact with cancer risk, heart disease, or neurodegenerative conditions. NASA is not ignoring these questions, they are just not at the stage where they can claim answers. The current goal is still send healthy adults, keep them as healthy as possible during the mission, and bring them home. For a Mars colony, that's not enough. You would have to bet an entire future population on biological conditions that are still mostly untested. Until we have hard data on full life stages in altered gravity and high radiation, multi-generation Mars civilization is speculation, not policy. The safest thing NASA can say right now is that human biology is tuned to Earth, and every step away from Earth conditions adds a layer of risk and unknowns. And human biology isn't the only human factor. Even if you could keep bodies functioning with exercise and careful medicine, you still have minds under pressure. Small crews, tight spaces, long delays, and the knowledge that help is months away. So the next question is, if the body is under strain already, what happens to human psychology and group dynamics when you lock people into a Mars habitat for years, with delayed and sometimes cut-off contact from Earth? NASA does not treat isolation and confinement as background issues. They list them as a first-order hazard for Mars missions. Crews on a Mars trip will be more cut off and more boxed in than almost anyone on Earth ever experiences. The habitat is small, the outside is lethal, and the same few faces are around you every day for years. NASA links this directly to sleep loss, disrupted day-night rhythms, constant workload, performance drops, mood problems, and health impacts. That is already a serious risk, even when you pick highly screened professionals who train for this lifestyle. Scale that up to a colony with families, kids, unequal workloads, and much messier personal histories, and the social difficulty grows fast. Inside a Mars base, there is nowhere truly outside to cool off. Conflicts don't have natural release valves. If two people fall out, they still have to share air, food, and workspace. If someone burns out, the team can't easily rotate in a replacement from a larger pool. Over time, small frictions can harden into open conflict. On Earth, we are used to solving that with transfers, mediators, or simply distance. Mars won't offer that. NASA's concern is simple. Human tension can degrade mission safety even when all the hardware is working perfectly. Communication delay changes how all of this plays out. On the ISS, if there's a technical or personal issue, mission control is practically in the room. Talk, advice, and decisions move back and forth in real time. On Mars, NASA's distance hazard work makes it clear that crews will have to be largely self-sufficient. With one-way delays up to about 20 minutes and round trips of 40 minutes or more, time-critical responsibility shifts from the ground to the crew. They have to diagnose problems, choose responses, and act without waiting for Earth to weigh in. That means a Mars team needs more local authority and more flexibility than any crew we've flown before. Procedures can't be rigid scripts that assume instant ground support. They have to be guidelines that smart people adapt in the moment. Psychologically, that's heavy. Every big decision carries the knowledge that you might be wrong, and that expert backup can only comment after the fact. For colonization, this is even bigger. It's not just a handful of highly trained astronauts making these calls, it's a whole resident population that has to live with a culture of autonomy under uncertainty. And sometimes it is worse than delay. NASA's deep space mission research points out that you may get full communication blackouts, up to roughly 2 weeks in some scenarios. For example, when the sun gets between Earth and Mars, delay means slow contact, blackout means none. For a crew, that's a very different psychological hit. Problems that would be stressful under normal conditions become much heavier when you can't even send a question and know it's been heard. A settlement that periodically loses live contact with Earth is unlike any remote place we have on this planet. Even in the most isolated bases here, you can usually get a message out quickly, even if physical help takes time. On Mars, there will be windows where you could be dealing with a technical emergency, a medical crisis, or a leadership conflict. And Earth literally cannot talk to you in real time at all. People have to adapt to the idea that for stretches of time, they're completely on their own, not just in practice, but in communication itself. NASA's analog missions exist because they know these human factors can sink a mission that looks fine on paper. Projects like Chapea and Hera put small groups into confined habitats, limit their food, simulate delays in communication, and load them with routine work. The point is to see how teams handle boredom, frustration, conflict, and long-term stress when escape is not an option. These aren't PR stunts. They are controlled tests to find out how often fatigue, mood problems, miscommunication, or broken trust start eroding performance and safety, even when life support systems are functioning. A Mars colony would inherit every one of those issues and then add more. Multi-year relationships, power structures, resource disputes, generational differences, and people who were born there and never chose the mission. There is no switch that flips from this is a stressful analog to this is now a stable society. The same stresses, confinement, monotony, unequal workloads, perceived unfairness, limited privacy, remain, just spread over more people and more time. This is where most Mars hype simply looks away. People talk as if Mars is mainly a transport and engineering challenge. Build the rockets, land the gear, seal the domes. NASA's hazard framework says that is only half the story. The other half is long-duration behavior and organization. On Mars, a colony does not fail only when air, water, or power systems break. It can also fail quietly, when leadership splinters, when cliques form and sabotage cooperation, when key people burn out and cannot be replaced, when disputes over work, risk, or resources turn into permanent fractures. Add delay and blackout to that mix, and outside mediation becomes weak. On Earth, if a remote base has serious internal trouble, higher authorities can step in quickly, by call, by visit, by replacement. On Mars, any outside authority is slow, distant, and mostly symbolic during a crisis. Real power and responsibility stay local, whether the people there are ready for it or not. So even if you imagine perfect hardware, perfect rockets, and perfect life support, you still face this question: can a small, isolated human society under constant stress stay stable for decades, when it knows that no one can come to the rescue fast and that the outside world is uninhabitable? And remember, the Mars environment does not just test minds socially, it also attacks from the outside as dust, chemicals, and contamination risks that never go away. Martian dust is not like the dirt on your floor or the sand in a desert. NASA treats it as a hazard category on its own. A surface crew will grind through it with rover wheels, blow it around with landers, coat their suits in it on every EVA, and inevitably track some of it back into the habitat. Unless defenses are extremely good, people will inhale small amounts, get particles into eyes and skin, and ingest traces through food and water. NASA's dust studies point out that this material can contain toxic perchlorates and related compounds that can enter the bloodstream through several routes. So dust is not just a cleaning chore, it is a combined materials problem, a medical problem, and an operational problem that runs every single day. Those same perchlorates are what make use local resources so much harder than it sounds. NASA's 2024 work on detoxifying Martian materials makes it clear perchlorates and chlorates are harmful to human health even at low levels, and they attack equipment as corrosive agents. That means the water you dig up from subsurface ice may arrive with chemistry you have to remove before it is safe. The soil you want to use for plant growth contains salts that can kill crops or stunt them badly. Dust that sticks to suits and gets inside can quietly raise exposure over time and chew on sensitive metal parts. Every time someone says Mars is rich in resources, the missing piece is that those resources come mixed with substances a human settlement really does not want. Because of that, habitat design has to treat dust intrusion as a primary driver, not as something you fix with a vacuum and a mop. NASA's human health and habitat work recommends high-quality air filtration systems, dedicated dirty zones, and possibly a separate airlock area between vehicles or EVA suits and the main living space. Suit joints and closures need special protection so dust cannot grind them down or sneak past seals. Floors, vents, and storage areas all have to be laid out with contamination paths in mind. Where does dust accumulate? How do you remove it? And how do you keep it from entering critical systems? On Mars, contamination control is not a side project for neat freaks. It's part of your survival engineering, just like air pressure and power. And while you are fighting dust and toxic chemistry from the outside, closed habitats create their own biological risks on the inside. NASA notes that microbes can change behavior in space and in sealed environments, forming different biofilms, resisting cleaning methods more effectively, and spreading more easily. The organisms that naturally live on human skin, in the gut and in the mouth move around the habitat with every touch and every breath. Pair that with stress-altered immune systems, which NASA also sees in long-duration crews, and you get a slow, shifting microbial ecosystem inside the station. That means a Mars settlement must think like a hospital and a factory at the same time. It's not enough to make sure pumps and fans are running. You need an environmental health discipline, regular checks on air and water quality, surface sampling, clear rules for hygiene, careful handling of waste, and fast responses to any sign of mold, biofilm, or unusual contamination. If that is neglected, you can end up with chronic infections, allergies, or degraded system performance from slime and growth in filters, pipes, and tanks. In a closed loop, those issues don't drift away, they circulate. Put all of this together and you get a sharp contrast with Earth. Here, the line between outside and inside is forgiving. Outside air is breathable. Rain and rivers help dilute many contaminants. If dust blows in, you clean it up, and usually the worst consequence is irritation or allergies. On Mars, outside is low pressure, CO2 heavy, cold, dusty, irradiated and chemically hostile. If that outside leaks in, it's not a minor event. It can change the atmospheric composition, add toxins to water, wear down equipment, and raise long-term exposure risks. So the boundary between habitat and planet becomes one of the highest stakes systems in the colony. Every spacewalk, every time someone cycles an airlock, every time a suit is connected or disconnected, you're stressing seals, moving dust, and risking a little bit of outside getting inside. Each of those cycles is part of the risk budget. Over years, thousands of those small events add up. A tiny recurring dust leak that would be annoying on Earth can be a genuine threat on Mars. By this point, the pattern should feel clear. Mars keeps forcing more and more systems into the must not fail category. Environment, distance, radiation, landing, logistics, life support, power, ISRU, food, biology, psychology, contamination, all of them critical, all of them coupled. And there is still one more layer that most colony talk skips almost entirely: the legal and planetary protection rules that NASA is bound by. Because even if you solve the engineering, Mars is not a completely free playground. There are treaties, contamination limits, and unsolved governance questions hanging over any attempt to settle it. Mars is not just an engineering project. It is wrapped in law and planetary protection rules that NASA is required to follow. NASA's own directive on biological planetary protection for human missions to Mars points straight back to Article 9 of the Outer Space Treaty. Under that treaty, the United States has to avoid harmful forward contamination of Mars and harmful backward contamination of Earth. Forward contamination means taking Earth life to Mars in ways that could interfere with native environments or future life detection science. Backward contamination means bringing something back from Mars that could harm Earth's biosphere. That alone makes "let's just go colonize" rhetoric look too simple. Any real NASA-linked activity on Mars is not just a technical and financial act. It's a tightly constrained biological act under international law. Robotic missions already live under these rules, but they're relatively easy to sterilize. You can bake components, use harsh cleaning methods, and accept design compromises to reduce microbial load because the payload doesn't need to breathe, eat, or go to the bathroom. Humans are different. People are walking ecosystems. They constantly shed skin cells, hair, bacteria, and viruses. They generate liquid and solid waste. Their habitats leak tiny amounts of air and moisture. NASA's Mars Planetary Protection Directive has whole sections dedicated to contamination from human presence. Spacecraft that orbit Mars, land on Mars, or return from Mars with samples or hardware exposed to the environment. That means NASA already treats put humans there as a fundamentally different contamination category from put a robot there. The moment you send crews, you're injecting vast numbers of Earth microbes into a place that may still preserve evidence of past or even present life. You're also creating new paths for Mars material to reach human bodies, suits, and inside surfaces, and potentially to come back toward Earth on return vehicles. Colonization, which by definition means more people, more activity, and more industry, multiplies those contamination pathways. And the rules for all of this are not finished. NASA's 2024 work on Mars surface systems, including power, openly notes that the agency is still developing specific planetary protection guidelines for human Mars missions. Their own seminar series in 2024 points out that there are still major knowledge gaps to close before a human presence on the Martian surface can be fully planned under planetary protection standards. That's important. One of the main governance frameworks that will shape how humans can legally act on Mars is still being figured out. It's not a mature, stable rulebook. Yet a lot of colony talk breezes past this, as if the only thing missing is a big rocket and some habitats. Science and settlement goals can point in different directions, and NASA's language quietly acknowledges that tension. If Mars still holds good records of ancient life or prebiotic chemistry, maybe preserved in ice, subsurface deposits, or old lake beds, then uncontrolled human activity could erase or contaminate exactly the evidence scientists are trying to study. Drilling, building, dumping heat and chemicals, leaking microbes, and moving large amounts of dust all change the environment. NASA's planetary protection principle is that exploration should proceed while avoiding harmful contamination. But a colony is not a clean surgical explorer. A colony spreads a biological and industrial footprint over time, which makes it harder to keep any region pristine for high-value science. So you get a built-in conflict. On one side, the push to expand human presence, build infrastructure, and tap resources. On the other, the need to protect key areas from contamination so we can answer basic questions about life in the universe. That conflict has to be managed somehow, by zoning certain areas off limits, by limiting what activities are allowed near sensitive sites, or by putting strict rules on waste and emissions. None of that is simple to enforce on a different planet, especially if private actors and other countries are involved. And that points to the bigger gap. A real colony would need a full legal and governance regime that simply does not exist yet. NASA's current rules deal with things like bioburden limits, cleanroom procedures, sample return handling, and mission approvals. They do not form an interplanetary civil code. A sustained settlement raises whole new classes of questions. Waste disposal. Where can a colony dump solid and liquid waste? Are there protected zones you can't contaminate? Land use. Who decides where bases, mines, reactors, and farms can be built? How are conflicts between groups resolved? Mining and resource rights. If a company or country extracts ice, minerals, or gases from a region, do they gain any exclusive rights? For how long? Environmental stewardship. What counts as harmful contamination once industry scales up? Are there Mars parks or protected basins that must stay untouched? Return quarantine. If people and materials come back from Mars, what level of isolation, testing, and decontamination is mandatory to protect Earth? For how long? Governance and law. Which laws apply inside a habitat, inside a multinational base, or at a privately run facility? How are crimes, labour disputes, or negligence handled? Right now there are high-level treaties and some national laws that touch on pieces of this, but nothing close to a full tested framework for a multi-actor Mars civilization. NASA's own documents stick to what they directly control: mission design, contamination limits, health and safety standards, and compliance with existing treaties. They do not and cannot lay out a full set of civil rules for property, citizenship, policing, or environmental law on another planet. That is bigger than any one agency. So when someone talks about a Mars colony soon, they are skipping not only the hard science and engineering steps, but also the institutional steps. It's not just build the rockets, get volunteers, set up domes. It's rewrite how we handle planetary protection for humans, agree on new legal regimes with other countries, define what responsible settlement looks like, and then enforce it at an interplanetary distance. We are nowhere close to having that in place. All of this feeds back into the main point. NASA's own realities check is deeper than one dramatic quote. At every layer, environment, distance, radiation, landing, logistics, life support, power, resources, food, biology, psychology, contamination, and now law, the picture is the same. Exploration may be possible. A self-sustaining colony is still far beyond what has been proven, and on top of all of these immediate hazards sits the biggest long-term claim of all. Can we ever make Mars truly Earth-like, or even close enough that people can walk around without life support? Terraforming is where NASA draws one of its clearest lines against easy Mars colonization. In 2018, the agency released results from NASA-sponsored research on whether we could fix the Martian environment by releasing greenhouse gases, mainly carbon dioxide, to warm the planet and thicken its atmosphere. The conclusion was direct. Transforming Mars into a place astronauts could explore without life support is not possible with present-day technology, because Mars does not have enough accessible CO2 to make a thick, warm atmosphere in any practical way. In simple terms, the easy version of the dream, just release trapped gases and walk around in shirt sleeves, is already ruled out by NASA's own analysis. That matters because a lot of popular Mars optimism quietly leans on that idea. The story goes like this. Mars has plenty of frozen CO2 and other gases in the soil and polar caps. We release them with machines or mirrors or nuclear devices. The atmosphere thickens, the planet warms up, and everything else gets easier. NASA's work cuts that off at the root. When they actually counted how much usable CO2 is there and how much warming it could provide, the numbers came up too small. Even if you mobilized what we can realistically tap, you still would not get to a pressure or temperature where humans can safely breathe outside or where liquid water is stable on the surface without heavy protection. The reason ties into Mars's history. NASA's MAVEN mission and other studies show that Mars used to have a thicker atmosphere, but over billions of years the solar wind and radiation stripped a large fraction away. NASA reported that about 65% of the argon that was once in the Martian atmosphere has been lost to space, and that most of the planet's carbon dioxide was also lost through processes like sputtering and escape. In other words, the easy atmospheric reservoir people hope to unlock is mostly gone. Mars had an atmospheric advantage long ago and then lost it. The planet we see now is the leftover. So the idea that we can simply release trapped gases and quickly rebuild an Earth-like environment runs straight into this planetary history wall. The accessible stockpile just isn't there at the scale needed. To build a new thick atmosphere, you would either need technologies far beyond anything we have today, things like planet-scale gas imports, massive long-term industry, or advanced methods for holding onto light gases, or you would need to discover some currently unknown huge reservoir of greenhouse gases. NASA's public stance is clear. With the knowledge and tools we have now, large-scale terraforming is not feasible. That helps explain why present-day Mars looks the way it does. NASA's recent science descriptions call Mars frigid and hostile to life at the surface, even as rovers search for evidence that the ancient planet might once have supported life. There is a sharp difference between past habitability and present survivability. Billions of years ago, Mars may have had lakes, rivers, and a thicker atmosphere. If microbial life ever existed, it might have emerged in that era. But a near-term colony would not be living on that ancient world. It would be living on modern Mars. Thin atmosphere, intense radiation, cold temperatures, dust, and chemically harsh soil. For colonization, that distinction is brutal. Ancient habitability does not fix current radiation. It does not restore lost pressure. It does not remove perch laurets from the soil or dust from the air. It mainly tells us that life might once have had a chance there, and that today, any remaining pockets of interest are exactly the kind of fragile sites you don't want to contaminate with heavy human activity. Terraforming as a way to solve Mars and make everything easy is off the table with current technology. You are left with something much harder: surviving inside protected bubbles on a world that is going to stay hostile for a very long time. So take a step back and connect all the pieces NASA has put on the table. Their own documents and data tell a consistent story. With enough advances, human visits to Mars may become possible. Small crews, carefully designed missions, strict life support, and high but managed risk. After that, a more sustained outpost might appear, still heavily dependent on Earth for spares, expertise, and critical supplies, but using some local resources and better recycling to stretch the logistics chain. But a self-sustaining colony, one that does not depend continuously on Earth for rescue, key spare parts, advanced medicine, and high-value industrial products, runs straight into stacked barriers. Radiation alone pushes against current dose limits. Entry, descent, and landing for human-class masses are still under development, not routine. Transportation and logistics are punished by distance and mass at every step. Life support has to run almost perfectly for years as a closed artificial ecosystem. Power has to be reliable and repairable under dust and cold, which is why NASA picked nuclear fission over solar as its primary surface source. ISRU is at early demonstration scale, not industrial scale. Food systems for even small crews are still being tested in analogues. Human biology in low gravity and high radiation is not solved, especially for full life cycles. Isolation, delay, and occasional blackouts turn every mission into a psychological and organisational stress test. Dust and toxic chemistry attack both people and hardware. Planetary protection rules and legal gaps add another layer of complexity. And in the background, terraforming, the one big idea that might have changed the whole game, is not realistically available with anything we can do now. So what is NASA actually saying about colonizing Mars? Not that it's forbidden forever, and not that humans will never go. The message is more precise, and in some ways more sobering. Based on current evidence, a self-sustaining Mars colony is far beyond present human capability. The planet is not just far away, it is fundamentally hostile across all the domains that matter: atmosphere, radiation, power, biology, logistics, psychology, contamination, and law. NASA's real work is focused on the first steps of exploration, proving we can get there, survive for a mission, and come home alive. The honest closing line is this: NASA is not closing the door on Mars. It is showing piece by piece why colonizing Mars is still out of reach. The technology, the biology, the logistics, and the governance are not there yet. Until those gaps close, Mars is not a second Earth waiting for us. It is an extreme frontier that might allow brief human visits, while a true civilization there remains unproven and, for now, impossible with what we actually have. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.